And so here we have more advanced algorithms. And I just noticed in the Discord chat, someone called them algorithms, and I'm disappointed I didn't come up with that myself, but I love it. Whoever said that, you're smart, good on you. And that is now the name of this course, Algorithms and Theoretical Computer Science. So first up, we're going to do a quick recap of what it was we studied last week. So we studied two algorithms. They were breadth first search and Prim's minimum spanning tree algorithm. And breadth first search is a way of finding shortest paths between two nodes in a graph. So if you're unfamiliar with the terminology of nodes and graphs, I can bring up a super cool notepad thing here. Ignore the stuff on the other side. I've covered it up with the chat. This stuff here, this is a graph. The circles with letters in them are nodes. The lines between them are edges. The lines have numbers on them, but for now, and that makes it what's called a weighted graph. But for now, we're just considering a graph without numbers on it, so an unweighted graph. So they represent these things, these graphs, quote unquote, they represent relationships between things. We covered this last week, but just good to have all the basics down. So a graph is a way of representing relationships between things. We use the example of air travel quite a bit, I believe. Also bullying and home layouts. So breadth first search is a way of finding the shortest path in an unweighted graph, a graph without distances, a graph which only considers like how many steps you have to take. So in the case of airplanes, it would be like if you made a graph which represented all the airports in the world and it just connected two nodes if you could fly from one to the other, then then a breadth first search would be what you use to try to find the path between two airports that uses the minimum number of stops. On the other hand, we then found out that you can weight graphs, meaning that you can involve like ideas of distance. For example, would you rather fly from New York, from New Zealand to Australia, or from New Zealand to New York? You'd probably rather fly from New Zealand to Australia because it like takes less time. And once you take that into account, that's where the numbers come from. Where's my cool graphic? Here it is. Basically, we just discussed graphs and why they're cool, and then we discussed breadth first search, which is how you basically start at the node and you expand out to get all the nodes that are one edge away from your start node, and then you expand out again to get all the nodes that are one away from that, so 2 edges away from your start node. You just keep on expanding out until you reach the node you're targeted at, and how many times you had to expand out will be the number of steps it takes in the shortest path from your start node to your end node. And then you had Prim's minimum spanning tree algorithm, which was a cool, greedy algorithm which we used to find a minimum spanning tree. So a spanning tree was, given a graph, it's like kind of a tree, a subset of the edges in that graph that contains all of the nodes in that graph as endpoints at least once. And a minimum spanning tree is, and if you got a weighted graph, you want to find like just the spanning tree with the least possible sum of all the edges in it. So in this case, that was the optimum. If you designed a different tree, it would certainly guaranteed have a bigger sum. So the sum here being 2 plus 2 plus 3 plus 8 plus 8 plus 7, 4, 1, 3. We covered all this last week, just making sure everyone's down. Now it's 7:05. So I think it's probably about time that we can start on the 2 remaining slides of this week. So let's get this started. So we're going to start with Dijkstra's algorithm. So who's heard of Dijkstra's algorithm? I can't just monologue, you guys. Someone aside from me got to speak. Otherwise, it would just be, I don't know, man. I would lose my voice. I would be unable to teach. One person has not heard of it. Another person has heard of it. Another person thinks that I talked about it at some point, and that is true. In fact, this fellow here is Edgar Dijkstra, who there's no way I'm pronouncing that right. But to be fair, his name has like a third of the alphabet in it, so like I don't think that I'm going to be pronouncing his name right anyway. But Edgar Dijkstra created Dijkstra's algorithm, and it is this garbage code over here, which I've then copy pasted over here for your viewing pleasure into this slide. So Dijkstra's algorithm, what it is it's an algorithm that basically does exactly what breadth first search does, but it works on weighted graphs instead of just unweighted graphs. So just for a little quick refresher, let's bring up a new paint window because I don't want to be using my other one. Dijkstra. Yes, indeed. Dijkstra. I hope. I'm not sure. I think it's a Dutch name, and Dutch people, man, I don't know. Some of their names are a bit whack. No offense if you're Dutch. Digikistra might be right. Anyways, we now have to get this massive bar out of the way. Always getting in the way. Say we make, oh, say we make a graph. It's going to have like, no, I don't want to turn on sticky keys. Thank you for asking. Just going to have like a couple nodes, and we're going to add some edges between them. Cool. Just having a good time. And some edges, no issues here. Just add another one. Let's add one here. So width first search would be used in this graph if you wanted to say take this here. Is there a fill bucket? Oh, there's a fill bucket. Lovely. If you wanted to say go from the blue node to the red node, the shortest path, i.e. the one that uses the fewest edges, would be the blue node, followed by these green nodes in order. This one, and then we reach the red node. So blue, green, green, red. That would be how you use breadth first. And the way you would use breadth first search for that would be you like spread out bit by bit. First, you consider all of the adjacent nodes to the blue node. That's just this one. Then you consider all of the adjacent nodes to this one. Oh, and also as you're going, you take note of the fact that it took you one step to get here. My God, is that white? That's awful. How do you do the font here? It took you one step to get here. Then you would just do that again. You would visit these other ones. This one, and note that it took you 2 steps to get there. It took you 2 steps to get there because you got there from the 1-step one, and then you took another step. And then finally, you would continue out and go from the 2-step ones out to the 3-step ones, this one, and this one. And that's actually all the nodes in the graph. And you would go, oh, that's pretty cool. This is now a perfect labeling of all of the nodes in the graph based on how long it takes you to get from there to there from the blue node. So to get to this node, it would take you 2 steps. To get to this node, it takes you 3 steps, and so forth. Not too convoluted, and hopefully not too difficult. I did just realize that there is a fill bucket, and it is so useful. Like, look at this. Last time what I was doing was I was like grabbing this pen and like scribbling all over them. I feel upgraded. I feel like a digital artist. Anyway, however, this problem can become somewhat more difficult when you're not just counting the number of steps you have to take, but you're also taking into account some other measure of distance. So let's clear everything out. I said let's clear everything. I can't clear everything out. This is so sad. I'll just use fill bucket again. Clear everything out. You go away. Oh, I actually can make him go away, but I think I'll just use the eraser for that. So let's give these some labels because that's something we can do. Say this is 2 long, 3 long, 2 long again, just 1 long, 3 long, 0 long. This edge has no length. It may appear to have length, but it actually doesn't. 1 long again, and 4 long over here. So if we now give these edges lengths, and by the way, I hope everyone is comfortable with like this pictorial representation. If you're not comfortable, tell me immediately in the chat. Is this someone told me in the chat? No, they've said wow moment for real, and it is a wow moment. Now, if we have these weighted edges, it's a little more difficult. We can't just spread out and go, we should go here, 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 as we did in the last one, because that doesn't work anymore. Here, here, here is actually suboptimal. That takes a total of 2 plus 1 plus 3 total distance traveled from blue to red, and that is 6, and that is not optimal. We can actually do it in less. So let's see, who can tell me? Prim's one doesn't work in this one. Prim's algorithm is used to develop a minimum spanning tree. So in this case, the minimum spanning tree would be, I think the minimum spanning tree would be, I'm just going to fill in the minimum spanning tree real quick with Prim's algorithm, mind you, with Prim's algorithm. We're going to start here because we can. And now we're going to take the minimum edge coming out of the green, and that'll be this 2, not this 3. So we take this one. Now we'll take the minimum edge coming out of the green. So out of 1, 0, and 3, it's obviously 0. Again, the minimum edge coming out of the green. It could be the 1. Oh, I should be highlighting these as I go. Sorry. Not that. We've done this one and this one so far. Now we'll take the minimum edge coming out of the green. It's actually both of these, this one and this one. It's two at once. We'll fill those as we go. And then we'll take the minimum edge coming out of the green. By coming out of the green, I mean the minimum edge between a green node and a node that's not yet green. And we would go zap. This is the minimum edge because 2 is less than 4. And then finally, obviously, we're just going to add in this final edge and we will be happy. And if you notice that some of the edges have been highlighted in green, that will be the minimum spanning tree. However, a minimum spanning tree is not the same as a shortest path. The shortest path between this originally blue and originally red, now all green, nodes, between these two nodes, does actually happen to be in the minimum spanning tree, but it, as a general rule of thumb, doesn't necessarily have to be the same. In fact, as a cool exercise, try to create a graph in which you do a Prim's algorithm, and then you take the two nodes in the tree. And in a tree, by the way, it's a general mathematical fact that if you draw up a tree, like, oh, no, like this, say, this is a very weird tree structure, but if you just imagine that there are nodes at the endpoints of these little lines I'm doing, if you draw up a tree and you take two of the nodes, say this one here and this one here, then there is only one unique way to get from one to the other without backtracking. So in this case, it would be this edge and then this edge. However, so you could create the Prim's algorithm minimum spanning tree, and then you could create the path. But in general, this is not actually the optimal, the minimum path. It is just the minimum spanning tree. There is a difference, and I highly recommend that you try to play around with some graphs on your own. Just make some random graphs, give them random edge weights, and just see if they, and then draw in their Prim minimum spanning tree, and then draw in their shortest path between two nodes, and see if they're the same. And I guarantee that you'll eventually be able to find counterexamples where they're not the same. But anyway, I've colored my entire thing green, and can I only go back so far? Oh no, I can only go back so far. This is so sad. I'm just going to file new because I cannot be bothered doing that all again. So the idea of Dijkstra's is pretty simple. We want to find those paths. In the case, no, I don't want to turn on sticky. Why do you keep asking me to turn on sticky keys? I don't want to turn on sticky keys. The idea of Dijkstra's is pretty simple. We've got a bunch of weighted edges this time, and we want to find the shortest path, where shortest means like smallest sum of all of the different edges in the path. So the shortest path is not necessarily in the shortest spanning tree is the thing. Oh, I've been, here we go, everyone in meeting. Not necessarily. But almost. They're very similar ideas, but they do solve different problems. So now, anyway, enough messing around. We are now actually going to, not sure why I made this again, but we're now actually going to apply Dijkstra's algorithm. So let's take a quick look at it. And this is a hilarious meme, so funny, that I found within like 3 minutes of Google searching Dijkstra's algorithm memes. And as you can see, the pigeon is walking around because he is stupid and does not realize that he should travel the shortest path. And instead is like trying to travel the longest path, apparently. It's rather unfortunate birds, pigeons. Anyway, this here is the Dijkstra's algorithm, and it's basically just a massive wall of text, and that is deliberate. You don't need to understand the massive wall of text. What we can do, though, is look at the wall of text, try to understand bit by bit what kind of stuff it's talking about. The coding language it's in, by the way, is not in any known coding language. If I were to put it into Python, Python would just be like, what are you talking about, man? This is not real. It's called pseudocode, and it's a way of like writing out code in a non-actual language, but so that you can read it pretty easily. Like in Python, these statements would probably have a bunch of brackets in them and look weird. But here we can just go, oh, for each vertex in graph.vertices, oh, so we just check every vertex in this group of vertices in all the vertices in the graph. And so, yeah, it's like writing code in English, but like a weird hybrid of English and code. Anyway, what we're going to do here is we're going to apply Dijkstra's algorithm. I'm just going to copy paste the whole of Dijkstra, if it will let me. I'm not sure that it is going to let me. That's very unfortunate. Oh well, we'll just read it off this. Can't copy paste from Google Slides into this, unfortunately. Very sad. Anyway. What we have here is a graph. with weights that I've created by taking a PNG and adding 2 extra nodes to it, being F and G. So what we are going to do is find not the distance from one node to another, because that would be too easy. We're going to find the distance from one node to all of them. In this case, I've selected node G because I don't know, I kind of like the letter G, it's in my name. So we're going to take this one here, G, and we're going to try to find all of the minimum paths from G to all of the others. So we'll record them over here. The minimum path from G to A, to B, to C, D, E, and F. And we will be able to do it. Minimum spanning tree, again, not quite, and not in order either. We're going to do them bit by bit. The algorithm we will use is somewhat different from the minimum spanning tree one, but does have its similarities. So the way the Dijkstra's algorithm works is we go through this. Let's just put this in slideshow so I can use the laser pointer. The laser pointer is quite useful here. The way Dijkstra's algorithm works is, you don't need this line. So first up, basically we create a thing called dist. We're not going to use priv here because priv is like kind of boring and not necessary here. Maybe we'll go into it after we're done with the basic ideas of Dijkstra. But we're just going to create a thing called dist. So for those who haven't worked in Python before, this symbolization here basically means that we've got a thing called dist, which is like a bank of information. And when we put something in square brackets, what it means is we're accessing that specific piece of information. So for each and every vertex, we call it v, and then we update the distance value of v to infinity, and we add v to a q. A q being, as we discussed in the last lesson, a data structure in which you put things in the top and things come out the bottom. Like a normal queue in real life. Things come in, the first thing in is the first thing out. So the first vertex that we add will also be the first thing that we remove from the queue. And we remove things from the queue down here. But first, we just initialize stuff, so let's go right ahead and initialize stuff. For every vertex, every single one of them, A, B, C, D, E, F, G, we're going to make its distance infinity. Nice, cool. There's a text, A, infinity. I'm going to copy that. B, infinity. I'm not going to copy it, actually. C, infinity. D, infinity. E, infinity. F, infinity. And amazingly, the distance from G to G is in fact infinity. I believe we changed that. Yes. As soon as we've done that, we realize, hey, wait a minute, this is a bit silly. The distance from G to itself is not infinity, it's 0, because like how far are you traveling if you just stand still? Not at all, right? So we're going to take that in and we're going to say, no, actually, it's not infinity. It is, I'm going to scratch that out. It is 0. The distance from G to G is 0. All the others are infinity. Distance from G to anything else is infinity right now. This is our best guess. We don't know anything about it because we haven't actually done any processing yet. We're just setting them to infinity because we know it's probably less than that. So much for that. Now we do the bulk of the code. So this here is what's called a while loop. So basically we're saying, okay, we're going to do this big chunk of, no, we do not want that. No, we very much don't want that. Where is he? Okay, here he is. Also no. We're making what's called a while loop here, while q is not empty. So q here is a q, and we're saying, okay, as long as q is not empty, we do this garbage, and then we check if q is empty. If it's not, we do the garbage again. Is it empty still? Nope. We keep doing this, and we just keep on going through this and down, this and down, this and down, until q is empty, and then we're done. And then we just give back the values. Return dist is basically just a way of saying, yep, you've got the right values now. Good on you. You're done. I play chess. Yes, I do play chess. Chess is fun. For some people. Anyway, while q is not empty. So while q is not empty basically says, get on with it, start doing something, and that's what we're going to do. While q is not empty, what do? We create a vertex in the queue, and the vertex is the one with the minimum distance. So right now, that is literally G, because 0 obviously is less than all the infinities, right? Like, hopefully we can agree that 0 is less than infinity. Otherwise, we might have some issues here. So this vertex U starts out as being U equals G at the start. So the start U is G because U is the vertex with the minimum distance at the time. And we remove it from the queue. I should probably create this queue now. I should probably create this queue. I'm going to say the queue is, right now, it is A, B, C, D, E, F, G. It's just all the nodes. No problem here. And now what it tells us to do is to take the vertex with the minimum distance and remove it and call it U. So that's exactly what we're going to do. We're going to use our eraser tool and remove G and make a variable called U and store G in it. So far we've done really nothing. But now here's the bulk of the code. No, not again. Where did it go? No. Okay, here's where it went. For each neighbor of U that is still in the queue, and we're calling these neighbors V, each one of them, you do some stuff. So, what are the neighbors of G, because G is U, that is still in... This is really beginning to get on my nerves. This is why I don't use Paint very often. What are the neighbors of G that is still in the queue? Well, everything's still in the queue aside from G, so it'll be just what are the neighbors of G? And that's F and E. F and E are the neighbors of G, meaning they're adjacent to it. Fe iron, yes indeed. So F and E are our relevant vertices here, and so we're going to run through them both. So first up, we consider F. We create a thing called alt, which is equal to the distance to U, which is G. There's a lot of variables here, and it can get confusing, but basically U is just the vertex we're considering at the time, and right now that's G. So the distance to U, which is G, which is currently 0, plus the length of the edge between U and V. And the length of the edge between U and V is the length of the edge between G, and I'm going to start with E because it comes earlier in the alphabet than F, and that is 44. So where's my text? So alt is equal to 0 plus 44, which is equal to 44. Okay, cool. So we create this alternative thing, and if it's less than the distance, then we update the distance to alt, and we update, well, this we're not doing, the prev thing. Every time you see the word prev, just ignore it. We're not doing that bit. So we update the distance to the alternative. So, well, the distance to E we can now say is 44. This is hopefully not a surprise, the distance between G and E being a 44. For now, at least, because we will change it. So the distance to E is 44. Not infinity anymore. Because, and the reason why we did this, by the way, very important, is because 44 is less than infinity. So we take this alt and we take the previously known distance value, and if alt is actually better than the previous distance value, we drop it down. And then we just keep going. So it's it for each neighbor of U, which is G, but we've only considered the one neighbor, which was E. We have to consider the other neighbor, which is F. So in the case of F, the alt is going to be different. It is going to be the distance, which is 0, plus the length of the edge between G and F, which is 11. So in this case, the alt is 11, is 0 plus 11, which equals 11. And of course, 0 plus 11 is less than infinity. So we're going to update F as well. And we're going to make it 11. If you're not following so far, that is completely okay. This is just like the brute part of the code, just so that we can understand like how this code works. And then basically, once we've done that, we go, okay, is Q empty? Nope, there's still A, B, C, D, and E, and F in the queue. So we still got stuff to do. So therefore, since we've still got stuff to do, we would go again, and we would do it all over again. So much for like the worked example bit. We're now just going to consider what it actually means. We're going to get back to the worked example after we just consider quickly what this underlying idea of the code is. So the idea of Dijkstra's algorithm is that basically at the start, we imagine that the distance to all the nodes is set to infinity. And then from there, we move on and we consider, okay, can we improve on that? So first up, we go from our start nodes to all the nodes beside it, and we go, okay, that's smaller than infinity. So we're going to update their distances to infinity. And then we just keep going. We just keep going through this queue, which, by the way, it's worth noting that we never actually add stuff to the queue. So I'm not sure why it is. Oh, sorry, still in the queue. That was me being stupid for a second. Sorry. Anyway, we go through the queue and we consider all of the things that are still in the queue. So in other words, all of the things that we haven't yet visited, because the only reason we take something out of a queue is when we visit it, when we make it equal to u. So we consider all of the stuff that we haven't yet visited, and we consider basically taking a little shortcut. Central idea of Dijkstra, sorry, I should have probably lit off with this, but the central idea of Dijkstra is when you've got a setup like this. And then let's make a little wiggly line. So, no, I wanted a wiggly line, thank you kindly. Good morning to the new person. We're just discussing Dijkstra's algorithm, pathfinding algorithm. So, the central idea of Dijkstra's algorithm is this weird little wiggly diagram here. If you are trying to find the distance between point A and point B, the fact that they're capital English letters has nothing to do with this over here. It's just an example. But anyway, if you're trying to find the distance between point A and point B, the central idea of Dijkstra is you can reroute through another node, C, and consider, okay, this will be equal to length L1, and this will be equal to length L2. And this over here will be the length of this currently accepted path is the current distance, which is the current distance from A to B. This is the current distance, and the central idea is if it happens that L1 plus L2 is less than the distance, then the distance shouldn't be what it is. It should be L1 plus L2. So basically, if you're taking a long path from A to B that goes like around through some other nodes, and then you find a shorter one that just goes through this one node, and L1 plus L2 happens to be less than the currently accepted distance, then you should make the currently accepted distance L1 plus L2. It's basically a guessing game of trying to refine your guesses and get a little smarter at each step. So anyway, well, I hope I can get rid of all this. Yes, okay, good. Okay, so anyway, back to it. While Q is not empty, we remove the vertex with the minimum distance. Okay, I cannot, there we go. While Q is not empty, we remove the vertex with the minimum distance. So among A, B, C, D, E, and F, which one has the minimum distance? The answer is F, because its distance is 11. The second best is 44, and then all the others are infinity, which is obviously way too big. It's not minimum. So we're going to remove F from the Q. Here's my eraser. Here's my eraser. We remove F, and we set U equal to F. U is basically a placeholder for whatever we just took out. Whatever we just took out of the Q. So we've now got U equal to F, and now we consider all of the neighbors of U. So now we've done this bit, we've removed it from the queue, and we've found the minimum distance one, and now we consider all of its neighbors that are still in the queue. All the neighbors of F that are still in the queue. So the neighbors of F are G and E, but G is actually not in the queue anymore, we've removed it. So we only need to consider E. So we consider E. So we're going to make a thing called V and call it, make a thing called V and set that equal to E. So we've got our two vertices V and E, and now we consider this alternative length from F to E, which is happening to be the length of current distance from G. By the way, in the thing where I drew the wiggly line diagram, A was the main source vertex, so here G. This is a lot of letters and probably a bit confusing, but basically the central idea here is we're trying to find a shortcut to E, because the distance to E is currently 44, and we're trying to find if we can go around that a little by going, say, on the shortcut to F. So vertices U and V are currently G and F. F and E. What am I even saying at this point? Vertices U and V are F and E. And we are going to consider the new alternative distance to E by rerouting through F. And that alternative distance will be the distance to F, so that's 11, plus the distance from F to E, so that's 3. And that's a total of 11 plus 3 equals 14, which does happen to be less than 44, which is our currently accepted distance to E. So we therefore update the distance to E to be 14, which was our new guess at a possible distance to E. And now we just keep going. While Q is not empty, we remove this vertex with the minimum distance. So right now that would be F because it has the minimum distance, but F is actually not in the Q anymore. So now it's E because that has a distance of 14. So we remove the vertex E from the Q and we set it in this little slot called U. And now we have to consider all of the neighbors of U that are still in the Q. So the neighbors of U, which is E, are G, F, and A, but as it happens, G and F are no longer in the Q. We've already considered them, so we just need to think about A. So V equals A. This is the only case we need to consider. In this case, the alternative distance is equal to the distance to E plus the distance from E to A, which is 44 plus 7, which is 51. So 44 plus 7 is 51, and this is a pretty good guess. Wait a minute, I'm stupid, I'm so sorry. Damn, I just forgot the entire idea of the algorithm. The distance to E is not 44. It was originally, but now we've considered it, we've found the distance to be 14. And so this will be 14 plus 7, which is equal to 21. And so 21 will be the distance from G to A, and as 21 is less than infinity, we can now update the distance to A to be no longer infinity, but now 21. Good fun. And this corresponds to, of course, going 11, 3, 7. So now, while Q is not empty, well, Q is not, as it happens, empty. There's still A, B, C, D, and we actually got rid of E in the last turn, but we've still got A, B, C, and D in the Q, so we're still going to keep going. The vertex that is in Q with the minimum distance will be A, because all the others, B, C, and D, are still infinity, but A is 21, which is less than infinity. So therefore, we're going to remove A and set U equal to, erase this, and set U equal to A. Now what we have to do is consider all of the neighbors of U. Hopefully we're starting to get into the rhythm of this a little. It's like most algorithms, it's pretty rhythmic. You follow steps. So U equals A, and V equals all of the neighbors of A. So we're going to, that have not yet been visited. And as it happens, that's actually all of them, B, C, and D. So we're going to start with B because we're just going to go alphabetical order, why not? B equals B. In this case, the alternative distance, I should erase this weird little garbage here. In this case, the alternative distance will be equal to the distance to A plus the distance to B. The distance to B is, of course, 10, but the distance to A, well, it is 11 plus 3 plus 7, and as we can see, that was 21. So the alternative distance will be equal to 21 plus 10, which is 31. And as it happens, 31 is less than the previously accepted value for the distance to B, which was infinite. So we'll update the previously held value for the distance to be 31. And now we keep going. So we're going to now consider the V equals C case because we're just going through alphabetical order through all the neighbors of A. So V equals C is what we're considering right now. So V equals C. What's the alternative distance going to be here? It is going to be the distance from G to A plus the distance from A to C. One continuous, and now actually, because I'm doing kind of a garbage job of explaining this, and as every garbage teacher does, they ask the class to help them out. So who can tell me what the alternative distance will be from G to C? Considering that U is A and V is C, who can tell me what the alternative distance will be? The alt value that we're going to be considering. "14 plus 7 plus 12 is correct, yes. So the reason, and indeed we've already stored this, so the distance from G to A, the best one we've found so far, it might not be optimal, though it is, but the best one we've found so far is 21, which was found by going G to F to E to A, instead of doing the more direct route G to E to A, because that was, of course, unfeasible because of this massive 44 here. So G, F, E, A had a total combined edge length of 21, so therefore it is the currently accepted guess, 21. And then we add on to that the distance from A to C, not by any fancy long-winded path, but just by a path of length 1, literally just the edge between them, which is 12. So the alt is 21 plus 12, which is equal to 33, yeah. And so we are going to update the distance to C from what it was, which is infinity, to 33. And notice again, by the way, we're only doing this because infinity is bigger than 33. If infinity was less than 33, we wouldn't update the distance to be something bigger than it already was. We're trying to store the minimum distance here. The minimum distance from G to each of these nodes. So now, we've done B, we've done C, and now we're finally going to deal with D. So, let's get on to that. We're considering A to D, so U remains as A, but V becomes D, and the alternative distance now, indeed, some similarities with the calendar being noticed, but the alternative distance, who can tell me what it is now? The alternative distance from G to D, not C. (21 plus 60 is correct. Okay. So 21 plus 60, and the reason why this is, again, I might be going into a bit too much detail on this, but the reason why this is because we're going 11, 3, 7. This is the currently accepted best path, the one that we currently think is the best. And that has a total score of 21. And then we consider the path from A to D direct, which is 60. And yes, that is 81, and it is less than the currently accepted value for the distance to D, which is infinity. So, of course, we're going to update that and make it 81. And now we are surprisingly almost done. So but we're not done. It's very important to notice that even though all of these have been visited once, so everything here has been like labeled. There's no infinities left here. Notice that. This is scribbled out. I might as well just erase it. There's no infinities left here. Why does the minimum spanning tree not work? I will address that question after we are done with Dijkstra. Sorry, boss. So we may have updated everything once, but we don't necessarily have the optimal yet. We just have some paths. For example, the path from G to D here is considered to be G, F, E, A, D. But of course, that is not the best we can do because G, F, E, A, C, D is better because it avoids this massive 60, instead opting for 12 and then 32, which is more optimal. So we're not done. We got to keep going until the queue is empty. While queue is not empty, we keep doing stuff. So we remove a vertex from Q with the minimum distance, and that vertex will be, well, actually, who can tell me? Who can tell me what the vertex will be? And I'm going to place a categorical imperative that a specific person in the chat cannot tell me. Yes, you're correct. It is not you. Because you have said basically everything, except for Helena, who said you play chess, which is true. So yes, who else can tell me what vertex we're going to be considering now? I will look really stupid if none of the 10 people in this class tell me. So please, God, I implore you. There's myself, and then there is Jessica. And those are the people who cannot speak. Everyone else can speak. Please. I beg of you. Who's got an idea? Which one we're going to be considering next? I'll put the algorithm code up on the screen quickly. Nope, not Sonic. Algorithm code is, we need to consider the vertex that is in Q and has the minimum distance. Vertex in Q with the minimum distance. So who can tell me what that is? All right, maybe no one. F is a good guess, but so F is the one in this list aside from G, which is like G, it's the start node, we're ignoring it. Aside from G, F is currently the one with the minimum distance from G. However, it is not in the queue. So the queue only contains B, C, and D. But F is a good guess because 11 is the smallest in this list listed here aside from 0. So yeah, but right now the only ones in the queue are B, C, and D. We've visited all the others. Anyone else got an idea? Exactly. Right on. And we now have our answer. Thank God Helena saves my class. So B is the correct answer because of B, C, and D, the things remaining in the queue. B is the smallest current distance, 31 versus 33 and 81. Yes, and someone else talked. Amazing, glorious day. So we remove B and we update U to be B. I'm a little low on time, but honestly, I'm quite happy spending this entire lesson on just this algorithm because this algorithm is like the central algorithm that I was trying to cover in this course. It is super, super useful. Uh, it's used in Google Maps, for example. It's used in the foundations of all the algorithms that are used to route packets of information through the World Wide Web. It's used just all the time. In fact, you'd be quite hard pressed to find some person somewhere that has not taken indirect uh, benefit from the invention of Edgar Dijkstra's algorithm in some way in their life. So anyway, getting a little off track, but now that we've got u equal to b, we need to consider all of its neighbors. That's a and c. So we're first going to consider v equals a, and then we'll consider v equals c. In the case of v equals a, the alternative distance will be the distance from g to b plus the distance. I may be stupid. I am again stupid. I love being stupid. It's a great way to. 3 people also. That's great. Stupidity is a great way to pass your time. But anyway, we're going to consider, sorry, all of the neighbors of B that are not in the queue, that are in the queue. Man, I don't know what's up today, but anyway, we're going to be considering all of the neighbors of B that are still in the queue. So currently the only things in the queue are C and D is not a neighbor of B, but C is. So we're just considering C. A cannot be considered because it is not in the queue. So we consider C. Now, the distance from G to B currently is accepted at 31, and the distance from B to C is accepted at 20. So therefore, the new alternative will be equal to 31 plus 20, which is equal to 51. So 51, that's a pretty good distance to C, but it's just not good enough because 51 is too big. The currently accepted distance to C is 33. That's longer, that's shorter than 51. That's better. If we were driving around in this graph, we don't want to go G, F, E, A, B, C when we could just go G, F, E, A, C and get there faster. So we've done a little calculation, but it was for nothing, and we're going to ignore the result of that. Nice, cool. And with that, we're actually done here because we've considered all the possible V for this choice of U. So now we do it again. There's still stuff in the queue. There's C and D. And so who can tell me now which node we're going to select? Where's my check on? He's vanished. So we're going to be selecting C and D, except for you, yes, because you're already too smart and evidently understand this, you cannot speak. It's awful, I know. So we've got C and D remaining in the queue. C is correct because C is the one with minimum distance. So we take the minimum distance thing out of the queue. Alina is popping off today, very well done, and we have 33 versus 81, obviously 33 is better. So we're going to take C out of the queue and set U equal to C. Having done that, we're going to consider all the possible V values, which are the things adjacent to C that also happen to be in the queue. And that's D. This is just D. D is the only one in the queue. D is the only one adjacent to C that's still in the queue. It's just D. So V equals D. The alt calculation here is, who can tell me what the alt calculation here is? And actually this time, I'm going to ban Jessica and Helena. I'm going to just keep cutting down. Everyone who is smart and interacting cannot speak. This is probably the worst way to run a classroom, but people who are not interacting but are still smart now have to speak. So the alternative distance between, oh, I'm sorry. No! Okay, so evidently, so here we're using what's called a Boolean expression. If a person is not smart or they are not talking, then wait a minute, what did I even say? Confused myself. But no, I'm not saying they're not smart, I'm saying they're not talking, but they are smart. And therefore, the people who are not talking but are smart, I suggest that they speak up. Because I know that there are at least 7 of you. If my mathematics serves me right. There are 7 people in here who can tell me what the new alternative distance is. So the way that we calculate alternative distance is by considering the distance, the currently accepted distance from G to our node, which is C, and then adding to that the distance from C to the V node, which is D. I may just go through alphabetically. I shall ask, oh, as host of the meeting, I apparently have the power to ask someone to unmute. I will do that. I'm not sure if it does anything. Hey, Victor has said something. I know it's weird. I don't know that you can do that before. Okay. Victor has said something. 33. What did you miss? Nothing much. It's all good. 33 plus 32 is 65. Let's see, is that correct? So the distance from G to C is in fact currently considered to be 33. And then the distance from C to D is 32. And that totals to 65. And yes, I was bullying people into talking, and yeah, it succeeded. Never let anyone tell you that bullying doesn't work. Wait, no, that's a terrible message. That's an absolutely terrible message to spread. Bullying doesn't work. Be good and don't litter and all that. But anyway, Hector is correct. The answer is alt equals 65. And with that, we can now consider, is this alt superior to the currently accepted distance value for D? Well, the currently accepted distance value for D is 81. That's bigger than 65. So let's wipe it out. Boom. We've wiped it out. It's now 65. And as it happens, that's all we can do because there's one thing left in the queue. And once we take that thing out to consider, once we take that thing out, U will be equal to that thing, but what will V be equal to? There'll be nothing left in the queue for V to be equal to. So we'll have nothing to do, and then the algorithm will end. And therefore, we now have a complete list in this graph of the distances from G to those nodes. So the distance from G to C, if you want to get there, you're not going to do better than 33. The distance from G to E, if you want to get there, you're going to have to do it in 14. You're not going to be able to do it in any faster. And that is pretty cool. I know, right? Yay. We did it. Congratulations, everyone. Bruh. But the central idea that we should take away here is that basically we start at a point and we consider all the distances to be infinity. It's like we've just started out in a room and we've turned on a flashlight and we're like looking around, oh geez, everything's dark in here, I don't see much. But then bit by bit, we start looking around. And so first up, we start updating things to be smaller than infinity. And then we start doing this like mechanism of bypassing an overly long path. If we have a candidate path between the start node, which I will label as the start node, and this given end node. This is not my sister. This is my mother. Anyway, good morning. Thank you for epic roasted vegetables. Anyway, back to it. If we have a possible path between a start node and an end node, and it has a certain distance d, and then we have another node over here. Well, it's not quite like this. It's more like it's basically like that. If we have like a start node, yes, this is a better artistic interpretation, and we've got some long path possibly going through multiple vertices to get to some other node, and then finally we have a separate node over here, and we've got this path here is this path here. So far, this squiggly path is optimal, and then we've got some other squiggly path from this node to this node. This one down here is the start node. And we're going to call these A and B because we can. So if we've got a path that's optimal from a start node to A, and then we've got a path that's maybe not optimal from start node to B with distance D, and the optimal one has distance dist A. And then finally, we've got this edge length here, which I'm going to call edge AB. If it is true that D is greater than edge AB plus the distance to A, in other words, if it's true that you can get to B faster by going to A and then to B rather than by going by your previous path, then you should probably go by this new path. That's the whole idea of Dijkstra. Why is that one so skinny? I'm not so sure. I'm never let people tell you that. Yeah, we're going to pretend I never said that. Anyway, it is now 7:51. My battery is running low. One moment. This happened last time, and so I've still left my charger cord upstairs in my bedroom because I'm terrible at like cleaning stuff up. That's another thing. Cleaning is bad. If you clean things, remind me tomorrow, if you clean things, you might put them away and then just have to get them out again. Whereas here, if I live in a cesspool in a pit, well, I'm not going to have to get things out again. It's optimal in terms of work done. Anyway, that aside, basically, that's the idea of Dijkstra's. Instead of the naive breadth first search, bam, 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 spreading out idea, it's a simpler, cleaner idea of like just if you've got a better path, then you probably take the better path. And yet, it's such a powerful idea too. I changed the sides of the brush. You might not be able to find anything. Why not? This is I'm not saying like why not? You are clearly wrong. I'm saying like why not? Because it is interesting. Because everything is scattered. What do you mean, boss? While you clarify what you mean, I will eat a piece of cauliflower. What do you mean? I believe my sister did have a hand in cooking it. Good on her. No, everyone has questions, and that is fine. Questions are good. Hmm. So that's Dijkstra's algorithm. And I've spent an entire lesson teaching this one algorithm because it is important to understand, because it is a super, super, super cool algorithm. So anyway, so much for Dijkstra's algorithm. Who can tell me what paradigm Dijkstra's algorithm is? All I am thinking of is yummy cauliflower right now, but I'm also thinking of paradigms. Who can tell me what the paradigm of Dijkstra's algorithm is? The design paradigm. So there's a lot of them. There's not greedy. That is curious because Dijkstra's algorithm is a greedy algorithm. I know, right? Dang. Because you have like you got like five paradigms, and if you just choose one at random, like you got a 20% chance of being wrong and a 80% chance of being right. But sometimes probability just flips on you. So the reason why Dijkstra's algorithm is greedy is because it's making these small local decisions. It's not like looking at all the nodes at once and considering the graph as a whole. It's just going, okay, can I do a little better than I was previously by going from A, B, C instead of just going from A straight to C? No, I can't because that's 30 and this is 12, so I should probably stick with A to C. How about can I do a little better than I was previously by going from B, C, D instead of going from A, D? I mean, sorry, instead of going B, A, D. Well, yes, I can because B, C, D is 52, whereas B, A, D is 70. Or can I do a little better going GFE rather than just going GE? Well, yes, I can because GE is 44, but GFE is just 14. And so it's making these small tier. Uh, does it grab the nearest one? Pretty much, yeah. It's grabbing the nearest one. At each point, you'll notice if you look at the code, at each point it is just noticing the ones. It takes the one with the minimum distance, so that's a hint for a greedy algorithm. If it's taking extremal nodes, like the one with the minimum or maximum distance or weight or something, it's probably greedy. And then it considers just the neighbors of that node in making its decision on updating the distances. It doesn't consider anything else. So it is definitely greedy, but here's the thing, it works. I slandered greedy algorithms a bit before because I made that weird little example of like the crab cakes or whatever. But if you actually apply Dijkstra's algorithm to the crab cake graph, which by the way, if you were to draw it, would be something like I don't know. If you were to draw the crab cake graph, I will not save this. If you were to draw it, it would be like start here, two possible paths. With edge weights, since we've got 4 minutes, that's easily enough to do this. We're going to label these A, B, C, D, and these correspond to good crab cakes, so that's plus 10, awful place, minus 1,000, Mediocre place, +0. Pretty bad crab cakes, -10. If we remember the crab cake example, we're starting at A, we want to get to D, and we pick up some crab cakes on the way. They're either bad or good. And then if we chose the good crab cakes, we go through the pits of hell. And if we chose the bad crab cakes, we go through like, I don't know, just a road, like a normal road, not the pits of hell. So obviously going to C, D is better, but I told you that greedy algorithms can't do that, but actually they can. They just have to be really well designed. And Dijkstra's is a really well designed algorithm. So if we were to real quick slam this out, how would we do it? Well, we would make a Q equals A, B, C, D. We'd make distances from A. The distances would be, the distance to A is 0. The distance to B starts at, of course, infinity. The distance to all of them starts at infinity, except for the source node, which of course is 0 away from itself. And then we would just go through an update. So the first one we're going to take out of the Q is A. And once we've taken out A, we consider all of its neighbors. So that's B and C. For each of them, the distances will be 10 and -10. Wait a minute, yeah, so the higher is the worse. So I will actually just swap these. I was being a bit silly there, but yeah, the higher is the worse. So this will now be -10 and this will be 10. Cool, no problems. Anyway, the distance to B will now be -10, which is less than infinity. And the distance to C, inf and unknown are the same, basically. As soon as, because you're never going to have an infinite graph, right? Like, if you're running into an infinite graph, you're probably doing some really big brain math. And we're programmers here, we generally run into like finite stuff. Google is big, for example, really big, like bigger than I could ever possibly imagine, or you could ever possibly imagine, but it is still finite. And so infinite is basically just a very fancy way of saying, oh, it's unknown. We don't know it yet, but we're gonna know it soon. And that's a good motto for life. Anyway, so B we update to -10 because that is less than infinity, or rather it is a known value and infinity is the unknown value. Very well pointed out by Helena. And C we will also update to 10. And then having done that, we just keep going with Dijkstra's algorithm. We pop out the next one, the one with the minimum, so that will be B, because -10 is less than 10. So we pop it out of the queue, we consider all of its neighbors. So B is U here. Its neighbors are literally just D. It's also got an A as a neighbor, but A is not in the queue. The only neighbor in the queue is D. So we consider U equals B, B equals D, and that happens to be, also this should be +1000. There we go. +1000 because positive numbers are worse. I was being a bit silly at the start, but I just flipped all the signs. Anyway, the distance, what it will be, the new, how do you say, what did they call it? The alt distance. What will be the alt distance here? When we're considering U equals B, I'm putting a direct message to you, and V equals D. Who can quick math me the alt distance? You are allowed to as well. Everyone is allowed to. Just bang, 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 bang. Let's hear it. Who can do it? B, considering we're at B and we're considering the distance to D, what is the alt distance here? So that's, if we remember the alt distance, like, Helena says that is 9990, and that is correct. It is the currently accepted distance from A to B, which is -10, plus the direct distance from B to D, which is 1000. So that's 9990. That does happen to be less than infinity. Big though it is, it is less than infinity. So we will currently update the distance to D to 9990. Now we've just got 2 left. First up, we consider C. So what are we going to do with C? We're going to pop it, well, actually first we should consider C or D. Which one do we pop out? The answer is obviously C, because C has a current distance of 10 and D has a current distance of 9990, which is bigger than 10, and we take out the small one. So in this case, U equals C, and the only one adjacent to it is V equals D. The only one adjacent to it still in the queue is D. So the alt distance here. Who can tell me what the alt distance here is? Really quick. Quick maths in your head. It is not 0, because this is not 0. That may have been a mistype. That may also have been a mistype. Everyone is mistyping, but yes, the idea is that it is 10. It is just 10 plus 0 equals 10. Nice. And is that less than 9990? And now I'm going to leave this as a general question. Who can tell me if 10 is less than 9990? Why is there a V? So V is just the name for all of the nodes that are adjacent to our current node that are also in the queue. And U is the name for the node that we're currently on. Sorry, I might not have made that sufficiently clear. I keep flashing this Sonic on the screen for like 0.5 milliseconds, but U is a vertex in Q with the minimum distance. And V is a neighbor. The V is the neighbor of U, and it also has to be still in Q. Yeah, those have just been the shorthand names that we've been calling them throughout. Anyway, we are actually done here. Like, we are actually done. It's crazy, but Dijkstra's algorithm has done what I thought it couldn't do, because there's only one thing left in the queue, and like once you remove that, there's going to be nothing. Once you remove that, U will be D, but V will be nothing because there's nothing in the queue, and V has to be in the queue, as you can see, still in queue. So we're done. And these are our distances. The distance from A to A is 0. The distance from A to B, optimally, is minus 10. The distance, so you can't actually go all the way around. What that's saying is you can't actually go all the way around and avoid the bad crab cakes because it would involve you going through pits of lava or whatever. So we avoid that. The distance from A to C is 10. That one's kind of obvious. And the distance from A to D is not 9990 because now we can update it because 10 does happen to be less than 9990. We can update it to 10 as well. And so the distance from A to D is 10. The crab cake problem is resolved, and we are all rather happy. Also, I just realized that both Helena and myself are incapable of basic subtraction, and I apologize to everyone for telling you that 1000 minus 10 was 999D. That is unfortunately not true. I am sorry. Anyway, with that little dose of arithmetic, we are now done for the day. Have a nice one. Yes, not so good at math after all. Very sad, very sad. But yeah, have a nice one. Enjoy your day, and I hope you all sleep well, get good rest, and prepare mentally and physically for the Kahoot that we will have next week. Kahoots are cool. The Kahoot brought you to tears. The Kahoot has brought Helena to cheat. Man, that is not good. Are you overwhelmed with joy at the Kahoot, or are you like, no, not Kahoot, no, worst of the worst? Could be either. And yes, our prompter, who is more competent than me, has told you all, thank you for coming. Agreed. Thank you.